This video has been supported by PCBWay. Hey guys, last year we were able to give this magnificent Fluke multifunction calibrator a well-deserved in-depth refurbishing. Now there is nothing preventing it from doing its job and spreading that sweet accuracy for another 30 years. Except maybe that there is no more accuracy left to spread. You see, even just opening the enclosure once and looking at the internals lets some of those volatile ppm escape. And the open heart surgery that we performed was much more impactful than that. So now the calibrator itself needs calibration and adjustment. Theoretically, it's not that difficult. The 5700 can combine its functions in various ways, allowing it to perform a full self-calibration of all 41 voltage, current and resistance ranges, using only 3 external standards. Fluke calls it artifact calibration, and it needs a 10 kilo ohm and a 1 ohm resistor, as well as a 10 volt source. Practically, we still depend on a calibration service provider, and only the biggest of those can afford high-performance primary standards, like a Josephson voltage standard and a Quantum Hall resistance standard. Those who can usually don't allow pilgrimage and camping on site. Just from a logistics standpoint, it doesn't make sense to take the costly, heavy, fragile calibrator to such a primary standard in person, just to let it sit there for a day or two warming up, and then to lose half of the ppms on the way back home due to uncontrollable temperatures and vibrations. What we need are rugged traveling transfer standards with at least a good short-term stability spec, to import accuracy before handing over to Fluke and all other devices which happen to use the same artifact calibration principle. Today we are going to look at the 10 volt one. Or should I say, 2 different 10 volt approaches. There is of course the easy way of just buying one. Fluke themselves have a long history of making extremely good battery-powered voltage standards. This one, the Model 732A, is one of their earliest. It's so old, in fact, that it has a dedicated 1.018 volt output for compatibility with Western cell systems. It is, however, Zener diode based and therefore much more robust and less drifty. The drift of this unit has been recorded for the last 30 years, and it came out to less than 0.1 ppm per year. An absolutely impressive track record, exceeding even the specifications of its successor by far. Until one fateful day in early 2020 where it was noticed that it had jumped 50 ppm at once.
Oh no!
Anyway, that's how it ended up on my bench for some diagnosis and preventive maintenance. Oh boy, am I excited about this. It's guaranteed to be interesting. Back here there is some seemingly mundane power supply stuff. Mains transformer, a battery charger circuit, and a battery pack made from individual 6 volt lead acid cells. These have been swapped in 2018, so most likely they are still good. I hope the old ones have been disposed of in a safe and eel-friendly manner. Their battery trickle charger, according to the service manual schematics, is actually quite primitive. In the hardware revision we are dealing with here, most of the circuit has been replaced by a UA723 adjustable voltage regulator with adjustable current limiting. A 1980s preview of what modern electronic engineering is going to be all about. Hope you don't mind if I do the obvious replacements off screen. We've got too much to do today to rerun the simple stuff. After a certain incident that you will hear all about in one of the next videos, I also added these mains filters to my list of always replace on first sight. They are not as bad as carbon composition resistors and electrolytic caps, because usually they don't take other components with them when they die. But they used to be filled with a kind of tar, and when that gets regurgitated out, the stench never leaves your instrument again. Apart from that, there is only one unusual feature on the battery charger assembly that I would like to point out to you. I'm not talking about these playful twisted pair traces coming from the mains voltage selector switches, enclosed in what looks like a leakage containment polygon. I don't even know if they do anything, but their destination, the guarded power transformer, is crucial. Let's say you have a sensitive mains-powered voltmeter and a mains-powered source in a different enclosure running on a different transformer. We've been taught that transformer secondary windings are completely isolated from everything else, but in reality there are always leakage resistances and interwinding capacitances between primary and secondary. They have played us for absolute fools. If you connect two mains-powered devices only with the two test leads you need for a voltage measurement or whatever, those ruthless leakage currents will do their best to flow through the test leads, not caring that they influence your measurements on the way. That's why metrology-grade equipment tends to have a separate guard terminal, connecting internal shields around the most sensitive circuitry and right through the mains transformer. This provides a preferential lower impedance path for those common mode effects to do their thing safely, far away from my measurements. For DIY endeavors or repairs, a guarded transformer with a shield between primary and secondary is of course not that easy to find, even though it's pretty simple to manufacture. Here is Ian Scott Johnston with an anatomy lesson. I'll link the full version below and we'll talk about DIY-friendly methods in the second part of this video. For now, back to Fluke 732A where guarding is already taken care of. There is one more small board in the rear, hiding a huge population of illegal carbon composition resistors. I was so relieved when I saw that our board was not yet charred to a crisp. This is called the regulator PCB assembly because its most important job is to regulate input voltages from mains or battery down to 18.6 volt, which is what the reference assembly likes. Personally, I don't really know what it sees in 18.6, I'm more of an 18.0 kind of guy. Oh well, whatever floats your boat. The electrolytic caps on here all measured fine, but after over 30 years of service, I think it's time to retire them anyway. Just like all their carbon composition henchmen, which will now become 1% metal resistors. Again, there is a noteworthy sub-circuit on this board. It's for the calibration indicator on the front panel, using Q7, a programmable uni-junction transistor. It's a kind of a reverse thyristor that becomes conductive when the anode voltage exceeds the gate voltage. It powers the in-cal LED permanently, until the supply voltage falls below a certain threshold. In that case, it is assumed that something bad happened, like battery empty or on fire. Either way, the internal temperature couldn't be guaranteed anymore, and a new cal is in order. Alright, time for us to leave the boring management area behind and to unbury the business end, the reference assembly. Fundamentally, this product is actually based on the same SZA263 Zener diode that's largely responsible for my calibrator's good performance. So how is it that this DC voltage standard used to be the official recommended calibration source for that calibrator? What makes it better? Well, it's more than likely that they are doing binning at the factory. With the creme de la creme going into DC voltage standards, the second best going into calibrators, the third into multimeters, and the rejects somehow surface on eBay eventually. But the underlying Zener diode is only part of what makes the 732A so good. Look at the size of this package. All that to put out 3 DC voltages. Of course, it's all about temperatures again. This aluminium coffin, surrounded by 40 mm of insulating foam material on all sides, is kept at 48 degrees C precisely, far away from expected ambient temperatures. Even if those are not terribly stable, at least there is no powerful fan to inhale the changes greedily. There are only these holes for the trim pots, breaching all the wonderful insulation. I don't like those at all, even if they are meant to be covered by cal stickers eventually. Strange construction. The cables all feel a bit brittle. I hope I can snoop around in here without breaking any. There are 3 major thermal effects at play that have to be managed for this assembly to achieve best performance. First, our old friend the thermocouple effect that can generate microvolts and therefore ppms when junctions of dissimilar metals are at different temperatures. A tinned copper circuit board, gold-plated Kova component leads, nichrome resistance wires, and platinum resistance thermometers. None of this can be engineered away easily. So, care is taken to heat everything evenly, with these orange silicone heat pads on all walls. Who would have thought that there were applications for these other than 3D printers? Then there is of course the actual Zener voltage temperature coefficient of around +2 mV per Kelvin in this case. That is elegantly compensated by a matched transistor base emitter junction in the same package. Guess what? -2 mV per Kelvin. That's the SZA-263 for you, and that transistor actually has another purpose in addition to that. And third, there is of course the resistance tempco of all the surrounding configuration, scaling and trimming resistors. Other than using the finest Fluke branded hermetically sealed wire wounds, there's not a whole lot one can do about that, I'm afraid. Vishay's bulk metal foil technology was not yet around at the time. But with precise enough oven control, even these few ppm barrels will do their job superbly. Oh no. What the fluke happened here? I thought we were looking at a world-class DC voltage standard and not a look mom no computer circuit bending victim. Either way, I don't think I'm going to attempt freeing the reference assembly from its tethers. Nah, I just swapped all the carbon composition enemies in situ. Basically all blue resistors are new, and should be good to go for more than 3 decades this time. The originals were mostly out of tolerance, but none drastically so. The only obvious problem I was able to find in here is this heat pad that has decided to separate itself from its wall partially. I don't think that can account for the 50 ppm jump that brought us in here in the first place, but I'm going to reattach it anyway. I've been told that after the 50 ppm jump everything was perfectly stable once again. That matches what I've found inside, nothing worth repairing. I've got no explanation either, maybe incorrect handling or a mistake during the last calibration. Either way, I don't want to inconvenience the sleeping ppms in here any further. With all the perishables out of the way, I'm going to leave it alone and observe a bit more. Just a few more quick thoughts on design details before we move on to Act 2 of this video. The resistive heaters are all made for 110 volt mains. Here they are driven by 24 to 30 volt DC, which slows them down significantly. Additionally, there is a shaping circuit made from capacitors and mega ohms, low pass filtering the proportional temperature controller even more. The reference assembly has 3 NTC thermistors arranged in a modified bridge configuration. My brain can't process this crazy construct and neither can a simulation, so I'm afraid we've got to take Fluke's word for it and trust that after 1 day warm-up time it reaches some kind of stable state. The reference circuit is also pretty complicated, but only because it's meant to be adjustable to 10 volt precisely. Most of the expensive precision resistors are only in here on an if-needed basis. They are used to add or subtract fractions of ppms from the output voltage without adding temperature coefficient or long-term drift. That cannot be done only by trim potentiometers because those just don't exist with sufficient stability specs. The fundamental circuit over here in the corner is a lot more simple, and I bet it would be a lot more stable without all the adjustment clutter next to it. The SZA-263 is often called ref amp instead of just Zener diode, because with its series transistor and its most important divider on the side, it can compare a voltage to its own in-house Zener diode, while putting out a differential error signal. Now who's the expert at eliminating differential error signals? Of course, an operational amplifier gets to generate that initial compare voltage at exactly the right level that satisfies our ref amp. This arrangement has an inherent immunity against all sorts of errors, and it needs so few external components to generate 10 volt directly. That might be its biggest advantage over the competition, the LTZ1000, whose list of mandatory external components is long and much fought over. Okay, that segue came a little early. I'm going to put everything back together and we'll start data logging with my most stable voltmeter, the similarly ovenized HPM7177. Let's hope that we won't catch any more jumps, and while we wait, I'll introduce you to my own Fluke 732A alternative. The SZA may be nice and compact and easy to scale, but our old friend the LTZ1000 has a few compelling advantages up its sleeve too. For example, you can officially buy it, from time to time. There is a lot of publicly available knowledge about it out there. Regarding the most questionable thermal cutout designs, top secret burn-in recipes, And of course the all-time favorite, creative applications that differ from what the manufacturer intended. Officially I don't claim to be any wiser, but I've seen a few well-working applications now, and I think it's time for me to try my own. I'm going to build an LTZ1000 based voltage reference with its normal drive circuitry, a fixed gain buffer amplifier to turn its 7.1 volt into 10, and I'm going to make it battery powered and ovenized for mobility. As far as possible I tried to use readily available ingredients. But because this plan started to take shape last year, the current shortages have not been taken into account. There are these mu-metal cans for shielding sensitive components against a broad band of electromagnetic interferences. Those can be combined with these hermetic feed-throughs that my friend Gigabecquerel has donated to the good cause. These are the real deal. Kovar, glass, Kovar, and gold-plated for maximum fanciness. With these we can fortify our EMI shielding cans and make them resistant against moisture and other chemicals. With a hermetically sealed module we might get around using Vishay's sealed luxury resistors. We do still have to rely on Vishay in the end because they also happen to make the lowest TZmu SMD resistors, which I wanted to use instead. But those are at least stocked by the larger distributors and don't have to be custom ordered. Having these superb VSMP foil resistors available in many different values on short notice is awesome and a major threat to my bank account. They might not have the unparalleled temperature coefficient of their VHP series, or the sempiternal long-term drift of their VHA series, but they just fit wonderfully inside my mu-metal can and inside my budget. What worries me a bit is that they don't have flexible leads, so thermal expansion of PCB materials and solder joints is handed right over to them. Not that their ceramic substrate couldn't handle that, but there is a chance of losing fractions of a ppm to stress. I can relate, but luckily this video's sponsor PCBWay has a very elegant solution to that. Flexible circuit boards. These are the first ones I've designed and ordered ever. At first I thought I was opening Pandora's box with new design rules, an unfamiliar purchasing process and a lot of caveats. But in reality it was exceptionally easy. The result is as beautiful as I had hoped. It's flexible yet durable. The substrate as well as the cover lace are polyimide, with much better dielectric strength, heat and chemical resistance than traditional FR4 material. PCBWay's intuitive ordering form makes it no different than preparing a traditional board, with all the familiar settings. They can manufacture up to 8-layer flexibles, with ultra-fine 0.06mm features on every one. What's more, they can attach these directly to normal rigid boards, giving you the designer immensely powerful tools for high-density, high-reliability interconnects, and so much more creative freedom. It's a fun material to work with and much less prone to delamination. Only modification after the fact is a bit tricky because it's easy to break through to layers below. Just don't make mistakes, Kappa. In addition to my reference and buffering circuits, I also ordered these heaters, which rely purely on trace resistances. Based on some napkin math, I expect their room temperature resistance to be 35 ohms. And sure enough, all of them came out within 10% of that theoretical value. Weird flex, but okay for PCBWay's precise materials and processing. This is what I made these laser-cut thermal interface adhesive pads for in the last video. I hope nobody saw that. I'm going to attach a heater to the mu-metal can with one, to replicate Fluke's proven thermal design. But not really. This package is different in almost every way, and I expect it to need some significant fine-tuning later. For example, we can sweep the oven temperatures in an attempt to find the flattest TZmu neighborhood, where slight deviations have the least amount of influence on the output voltage. Oh well, let's get it to work with a more heavy-handed temperature control method first. What do you think I should call this project, by the way? I was thinking either ADR1002, as a nod towards a certain semiconductor rumor that inspired this whole thing, or LTZmu, but then I would feel the need to keep you waiting for a few years before releasing. I'd love to hear your suggestions in the comments. The mostly SMT construction makes population quick, easy and scalable, you know, if we were to turn this into a real product. The two leaded components, the LTZ1000 and its most important temperature configuration voltage divider, I couldn't really optimize away, but they need some fingertip feeling, as Germans like to say, to solder them correctly anyway. That's not great for production at scale, but not as bad as the finishing touches. Here's that mu-metal bottom cover. For lack of a better method, I'm going to have to hand solder each and every one of those hermetic feed-throughs. And I'm afraid I have to overdo it because I don't have a way of testing hermetic seals for leaks. The LTZ1000 for this module has been carefully selected, aged and tested in a different circuit before. This way, if my measurements reveal a problem in the end, I can be reasonably confident that the buffer is to blame, and not the voltage reference itself. Not a terribly unlikely scenario if I'm being honest. The fundamental circuit that generates ultra-stable 7.2 volt is pretty much the same that everybody else uses. Ultra-stable amplification, however, with fine trimmability and short-circuit protection was a bit of a challenge. Basically, a voltage divider with a 2:5 ratio gets you reasonably close. But more zeros after the decimal point are costly. I've reserved a lot of extra resistor footprints on my flex PCB, as well as 2 jumper links to configure either trim up or trim down. This trim resistor, if needed, can be connected from the outside to 2 of our hermetic pins. Fair warning though, these guys are all very influential, so if they ever decide to drift, it will be detrimental. It's likely that we could achieve better stability without all this trimming stuff. At a lower price too. Those blue SMD resistors are the 0.2 ppm per Kelvin Vichet ones. They are between $10 and $20 in single quantities. And the plastic molded Z202 ones are even more expensive, but I had those lying around before. Of course, no revision 1 circuit board is complete without a few botches. For example, the LTZ driving op-amp must be a single supply one, otherwise the circuit won't start. It took me a while to fine-tune this thing to 10 volt with 3 zeros behind the decimal point, using the limited selection of precision resistors that are available immediately. If needed, further adjustments are possible from the outside. Outside is also where I happen to store the goodest of the good stuffs, which cleans circuit boards better than anything I've tried before. It can clean plastic IC packages right off the board, so I wouldn't recommend it unless absolutely necessary. I will apply a few fixes to the project, then I'll upload it and link it below. But don't build one just yet. Instead, let me collect a few weeks worth of data first, to see if a doubly ovenized LTZ1000 and stress-free mounted hermetically sealed SMD foil resistors do actually work as nicely as they sound. I'm quite confident in the short-term stability for which I made this thing. That way I could ship it around to friends in Europe or take it to meetings myself. But I'm not delusional enough to think that I can beat Fluke 732A's recorded performance as easily as this. I'm not exactly loading my scaling resistors, but I am storing them at elevated temperatures, so I think we have to expect some low-to-life drift after thousands of hours. Let's press on regardless, with thick boy thermal insulation being such a prominent feature of Fluke 732A. I was sure I needed that too, so I bravely started CNC machining some styro dur. Just letting a hot mu-metal can sink into the material would have worked too, although that leaves some dense molten material around the can, which diminishes the insulation capabilities a little bit. It wouldn't have mattered, because turns out my first insulation attempt was way too good. Embedded in this foam shell, a single LTZ1000 and 3 op-amps were enough to push the internal temperature beyond 45 degrees C, just by self-heating in normal operation. I was thinking of setting my oven temperature to about 40. How about some audio foolery to give our voltage standard that full-bodied tonality and a clear, uncolored timbre that Fluke can only dream of? We already have the magically aged components, oxygen-free copper cables, pricey high-performance mains filters, and arcane geometries on the circuit boards. This type of R-core power transformer is available under various stickers, from China directly or at DIY hi-fi shops. Its construction suggests that it is ideal to insert a shield between primary and secondary, for our Fluke-inspired anti-common mode guard terminal. But unfortunately, on closer inspection it turns out that it is not. There are primary and secondary windings on top of each other on both coils, for easier reconfiguration of 110 and 220 volt, and also to improve the coupling coefficient, which makes the transformer more efficient. It's a pretty cool transformer, no doubt, but its interwinding capacitance is not going to be anything special, I think. Oh, never mind. There actually were shields between the primary and secondary windings. They were connected to a green-yellow lead, which usually indicates protective earth. They could have easily made them larger to cover everything while still not creating a shorted turn. But this is certainly better than any old off-the-shelf transformer. For maximum performance with least manual rewinding, I would just look at eBay, where you can pick up beauties like these for 10 bucks or so. There are also companies that wind transformers according to your specifications, including shields of course. The easiest solution, however, and yet one of the least obvious ones, if it's battery powered, you can just unplug it while in use. Where there's no connection to mains, there are no common mode troubles from mains. Hopefully. Instead of worrying about my standard burning down itself and the logistics company multi-million-dollar warehouse due to lithium battery failure, I think I'm just going to go with safer gel batteries. There are a lot fewer shipping restrictions on those, but in general, shipping powered-on electronics is always problematic, I think. The batteries, as well as my isothermal reference cube, fit perfectly inside this Schroff Ratio Pack Pro Air desktop enclosure. Can you tell that that product name has been chosen by Germans? The whole package will be a lot smaller than Fluke 732A. And I'll let it take its place in the long-term measurement now. A few more thoughts and details and then we can jump right ahead to the first results. The LTZ1000 datasheet application, as seen in 3458A multimeters and CERN ADCs for example, looks a bit intimidating at first. But it's not all that different from the SZA263 we've seen before. It uses this first transistor purely as a temperature sensor. The 13K 1K divider sets the base voltage to around 500 mV. When the transistor temperature rises, it draws more and more current, exactly until the collector voltage reaches 500 mV too. That satisfies the oven driver op-amp and it turns off the heater. The oven circuit is neither perfect nor almighty. So to make what little temperature variations there are less influential, the LTZ uses the same compensation trick where a -2 mV per Kelvin base emitter junction is added to the +2 mV per Kelvin Zener diode. It's neat, widely used and trusted, and clearly good enough for some of the best voltmeters in existence. But what about DC voltage standards? Are there any trustworthy models with LTZs inside? Other than my recent creation, I mean? Oh, glad you're asking. There is a certain Wavetek 7000 series and it is immensely interesting. Unfortunately, the company was bought by Fluke and the model 7000 soon discontinued. There is not a whole lot of info about them out there, but the EEVblog forum members are digging deep. Their answer to the common mode issue seems to be a special DC to DC converter, with a custom transformer whose primary windings and cores are encased fully in a conductive plastic shell. The conductivity has to be high enough to provide good shielding against interwinding capacitance. But it can't be too good lest it become a shorted winding that loads down the whole transformer. In the LTZ and buffering department, they are relying heavily on these arrays of equal resistors. By connecting multiple elements in parallel, slight deviations of the individual are of little consequence. And if all are truly equal, ratios are maintained no matter what. When I was talking about my heavy-handed temperature control method earlier, I was thinking about this. At Wavetek they were able to get great performance out of mostly affordable components. Even without brute force ovenizing the whole thing, much less hermetically sealing it. A big part of why that works so well for them is a resistor connected to LTZ pin 3, the Zener cathode. To test this, I disabled completely the heater circuit in one of my LTZ boards and instead took control over it with the Arroyo temperature controller. It was so brutally hot here at the time it hardly needed to supply power to reach those higher temperatures. But this made it possible to sweep the package temperatures while recording the LTZ output voltages, with different resistance values upstream. Here's what I got. With 20 ohm above and 120 ohm below. At around 61 degrees, one can clearly see that the LTZ output voltage reaches a plateau. A peak, if you will, where the neighborhood is as flat as it gets and small thermal variations have little impact. So the most popular configuration with a 13K 1K divider that just so happens to configure the oven set point to 60 degrees C is popular for good reason. Otherwise I'm seeing approximately a 10 ppm shift in output voltage for every degree Celsius. That's not too special, but significantly better than what I was getting with a datasheet recommendation of no ohms above and 120 ohm below. 33.5 ppm per Kelvin on average. Now let's take a look at this completely random configuration of 25 ohm above and 120 ohm below. Whoa, Grafana's automatic scaling makes that look unremarkable, but lo and behold, that is 1 ppm per Kelvin. So, it looks like Wavetek and everybody else who is determined enough can influence the LTZ1000 Tempco. EEV block forum member Branadic has demonstrated that that is possible down to fractions of a ppm. If a nearly perfect 0 ppm was reached, one could forget about the LTZ1000 heater altogether. I think this works by balancing the positive contribution of the Zener Tempco versus the negative one of the base emitter junction. We are taking influence away from the Zener diode by increasing the resistance in front of it, exactly until the natural mismatch between the two semiconductors is accounted for. Putting it that way, it should be obvious that this method is a bit of a double-edged sword. I wouldn't splice it into all existing LTZ circuits generally, because the influence that we are taking away from the Zener diode now rests on the shoulders of resistors. The 13K 1K voltage divider that used to be the most critical part no longer matters all that much. Instead, the circuit is now dominated by, I guess, the 70 kilo ohm one and our new so-called above resistor. I guess it would really work best in combination with Wavetek's statistical resistor network method. I just wanted to mention these fascinating ideas briefly and leave a mental note for myself that I'll have to try them someday. For now though, my heavy-handed flex PCB employs none of them. Alright then, let's get to the results finally. The Fluke 732A preventive maintenance actually took place last year, and I've monitored it intermittently since then, both using voltmeters and calibration reports generated by Fluke 5700. Not even a hint of another jump appeared since then. If anything, the two Flukes seem to agree with each other too closely, as if they are conspiring to save each other's skin. This, by the way, is why I was questioning the external trim capabilities of both the standards we've seen today. All devices that matter give you the opportunity to enter the precise value of the reference that's used. It has been only 7 days since the last calibration this time, but this is kinda sus, don't you think? Only something like a handheld multimeter will ask you to deliver the calibration values on point. And then that isn't something that one would use a fixed standard for. In the 0.1 to 10 Hz noise discipline we are getting 1.88 microvolt peak to peak or 192 nanovolt RMS. That's about 1/5 of their datasheet specification and therefore slightly suspicious again. But then again, the calibrator had 2.1 microvolt peak to peak, so we're in the same ballpark. Here are some graphs over the 9 most temperature-stable days in recent history. We are seeing day-to-day variations of a little more than half a ppm. The blue markers are self-calibrations of the voltmeter I used. Could I perhaps interest you in a video about that? In the end we are arriving at exactly the same value we started out with. That is looking very promising, but ideally I should have an entire coterie of standards to compare to. Unfortunately, my Flex PCB has not yet recovered from the shock of having been assembled a week ago. It is still happily losing ppms on a daily basis, but at a surprisingly steady rate. Hey, if it never settles down, at least it's predictable. I endured the suspense for another week and was rewarded with a capture of the one and only turning point. At this time the reference was powered by a benchtop PSU, so it's a bit more noisy than it has to be. Here I switched over to power from an imbalanced pair of batteries, and was promptly rewarded with a huge jump. We've got a poor power supply rejection ratio and probably need a better pre-regulator like Fluke. That also contributes to what looks like long-term drift in this plot. The positive battery discharges faster and makes the imbalance worse. In the next version I'm probably just going to ditch the 4-wire force and sense outputs. That way I'm going to need fewer expensive hermetic pins, one less op-amp and one less power supply rail. That will also make the self-heating a lot more manageable. If only I could stop changing stuff for a few days. I'm pretty sure I would have made it to 0.4 ppm per day already. Oh well, this is the best I have for today, but I'll keep you updated. What do you think we should do next? Resistance standards or a multimeter repair? We had quite the information density today, so if something needs more clarification, please leave a comment. Sometimes I miss the forest for the trees. Thank you for watching. See you next time.